Roadmap to Clean Energy using Laser Beam Ignition of Boron-Hydrogen Fusion. Introduction. For a thermal equilibrium plasma, the DT was the first choice of a fusion reactor because it reaches the high value of sigma V of 10 to the minus 15 centimeters cube per second for the lowest possible temperature at T equal 20 kilo-electron-volt. In contrast to the DT reaction, the boron reaction Hb11 reaction is very much less efficient under conditions of thermal equilibrium. The values of sigma V for the clean Hb11 fusion is so much lower that the gain is smaller by 5 orders of magnitude, a factor of 10,000,000. Such this option of fusion was usually excluded. This reaction reaches the large sigma V for temperatures at temperatures of about 600 kilo-electron-volt, and for laser ignition, a compression to 100,000 times solid-state density was considered as extremely difficult to be achieved using the conventional theories. The Hb11 reaction was of special interest because no neutrons were produced when the reacting H nuclei had lower energy than about 3 mega-electron-volt. Hb11 is then an environmentally clean reaction in contrast to DT. The aim of the neutron-free clean boron fusion was nevertheless highly attractive. That several proposals were developed by highly qualified experts. The only way out was to work at conditions without local thermal equilibrium (LTE) and using non-linearities. As conclude from proceed reach, a further advantage of the Hb11 reaction was the generation of 3 helium nuclei, which can be expected for producing an avalanche multiplication. For fusion, at consideration of non-thermal ignition, the laser was the ideal tool when using the result that the electric and magnetic fields E and H of a sufficiently intense laser beam cause an acceleration of nearly solid density plasma blocks without heating within a picosecond. Interaction to velocity above 10 to the 9th power centimeter per second. This numerical result of 1978 was exactly reproduced in agreement with the measurement by Savarelli with laser plus of picoseconds duration and powers between terawatt and petawatt, available 1996 and reported by Flores. This non-thermal ignition of solid-density fusion field was the result by Chu and by Bobin by initiation of the reaction to be produced within a picosecond. When hydrodynamic computations included next to thermal properties, the interaction of the laser fields resulting in non-linear forces dominating the generation of the plasma books and updating of the hydrodynamic computations and subsequently in full agreement with using a more detailed genuine multiple field code reproduced these measurements of ultra-high acceleration for DT fusion. Furthermore, it was then a great surprise when applied this for HB11 fusion that the ignition threshold for HB11 was elevated by 5 orders of magnitude above the classical values, arriving at the level of DT due to the non-thermal transfer of the laser energy directly into the ultra-high acceleration of the plasma blocks. Another advantage was the very fast measurement of HB11 fusion by using laser with those sound reactions per laser shot, followed by more than 1 million reactions, and then by 1 billion reactions. Competition with DT fusion confined that this could be achieved only by avalanche reactions. The detailed evaluation of these measurements based on elastic nuclear collision towards the exceptionally high HB11 reaction around 600 kV showed an increase of the gains by further 4 orders of magnitude. Based on these 9 orders of magnitude higher reactivity of HB11 at non-local thermodynamic equilibrium LTE conditions, a fusion power reactor was designed with picosecond laser pulse of more than 30 petawatt power that were expected to ignite 40 mg hydrogen boron for producing 300 kWh energy. The following section describe properties for aiming environmentally clean, low-cost, and sustainable energy production, and a list of research topics. Single laser beam ignition for fusion energy is an innovation for alternative conditions differing from the usual spherically irradiation by many synchronized laser beam. These developments were introduced in 2040 following the Patent Cooperation Treaty International Patent with the property of 23 March 2014 for the now progressing national phase. This development followed step by step for the first realistic option of an environmentally absolute clean reactor for the fusion of hydrogen with the boron isotope 11 for low-cost and sustainable large-scale energy generation. HB11 fusion is well known to avoid generation of neutrons that in all other cases of nuclear energy reactors are producing dangerous radioactive waste. The energy of the reacting hydrogen nucleus, the proton, have to have energies below mega electron volt for a reaction completely free from neutrons. The disadvantage of HB11 fusion is that it is about 5 orders of magnitude 100,000 times more difficult and was considered as impossible compared with the easiest fusion of heavy with super heavy hydrogen, deuterium, and tritium at conditions of LTE of the reaction plasma, and even DT fusion is still only close below broken despite enormous research using magnetic confinement FCF or inertial confinement ICF fusion. Against this fact of the impossible of HB11, the neutronic aspect attracted prominent experts to search for solution. This in principle could only be based on conditions without thermal equilibrium and without using non-linear effects. An example of studies of plasma different from LTE thermal equilibrium plasmas was developed for the dusty plasmas with similar problems to the HB11 fusion or non-neutral plasma. Attempts are using low-density plasma, where however no fusion reactions were measured yet, following the principle to use a non-thermal ignition of HB11 fusion by laser pulse led to measured high-gain Hb11 reactions, opening the option that ultra-highly accelerated plasma blocks with conversion of laser energy directly into directed plasma block motion in the range of solid-state densities. The present achievement is a 9 orders higher gain of fusion energy than classical measured. This is even higher than DT. The reason is the non-thermal ignition and the avalanche multiplication of the generated 3 helium nuclei of reaction in agreement with the theory. For the experiment,